Welcome to Slothful Slumber, the podcast where we transform the vast knowledge of the internet into a gentle lullaby for your mind. I'm your host, Luna Dreamwell, and I'm here to guide you on a journey to tranquility through the soothing cadence of Wikipedia articles. Each episode will delve into the most wonderfully mundane and sleep-inducing topics, helping you drift off into a realm of serene dreams. So find your comfortable space, close your eyes, and let the dull hum of information carry you into a restful slumber. Now, let's embark on tonight's voyage of tranquil learning as we explore a topic so peacefully uneventful, it just might whisk you away to the land of dreams. This Wikipedia article is titled Kelp. Kelps are large brown algae or seaweeds that make up the order Laminariales. There are about 30 different genera. Despite its appearance, kelp is not a plant but a stramenopile, a group containing many protists. Kelp grows in underwater forests, kelp forests, in shallow oceans, and is thought to have appeared in the Miocene, 5 to 23 million years ago. The organisms require nutrient-rich water with temperatures between 6 and 14 degrees Celsius, 43 and 57 degrees Fahrenheit. They are known for their high growth rate. The genera Macrocystis and Nereocystis can grow as fast as half a meter a day, ultimately reaching 30 to 80 meters, 100 to 260 feet. Through the 19th century, the word kelp was closely associated with seaweeds that could be burned to obtain soda ash, primarily sodium carbonate. The seaweeds used included species from both the orders Laminariales and Fucales. The word kelp was also used directly to refer to these processed ashes. Description: in most kelp, the thallus, or body, consists of flat or leaf-like structures known as blades. Blades originate from elongated stem-like structures, the stipes. The holdfast, a root-like structure, anchors the kelp to the substrate of the ocean. Gas-filled bladders, nematocysts, form at the base of blades of American species, such as Nereocystis luettiana, Mert, and Post, and Ruper, to hold the kelp blades close to the surface. Growth and reproduction. Growth occurs at the base of the meristem, where the blades and stipe meet. Growth may be limited by grazing. Sea urchins, for example, can reduce entire areas to urchin barrens. The kelp life cycle involves a diploid sporophyte and haploid gametophyte stage. The haploid phase begins when the mature organism releases many spores, which then germinate to become male or female gametophytes. Sexual reproduction then results in the beginning of the diploid sporophyte stage, which will develop into a mature individual. The parenchymatous thalli are generally covered with a mucilage layer rather than cuticle. Evolution of kelp structure. Under evolution by natural selection, seaweed were generally considered homologs of terrestrial plants, and an example of what is now called convergent evolution. Kelp are a brown algae, a phyla that is as distantly related to plants as amoebozoans are to the crumbs group, but they have evolved plant-like structures through convergent evolution. Where plants have leaves, stems, and reproductive organs, kelp have independently evolved blades, stipes, and sporangia. With radiometric dating and the measure Ma, unequivocal minimum constraint for total group Pinaceae, vascular plants have been measured as having evolved around 419 to 454 million years ago, while the ancestors of Laminariales are much younger at 189 million years ago. Although these groups are distantly related as well as different in evolutionary age, there are still comparisons that can be made between the structures of terrestrial plants and kelp. But in terms of evolutionary history, most of these similarities come from convergent evolution. Some kelp species, including giant kelp, have evolved transport mechanisms for organic as well as inorganic compounds, similar to mechanisms of transport in trees and other vascular plants. In kelp, this transportation network uses trumpet-shaped sieve elements. A 2015 study aimed to evaluate the efficiency of giant kelp, Macrocystis porifera, transport anatomy, looked at 6 different Laminariales species to see if they had typical vascular plant allometric relationships, if sieve elements had a correlation with the size of an organism. Researchers expected to find the kelp's phloem to work similarly to a plant's xylem, and therefore display similar allometric trends to minimize pressure gradient. The study found no universal allometric scaling between all tested structures of the Laminariales species, which implies that the transport network of brown algae is only just beginning to evolve to efficiently fit their current niches. Apart from undergoing convergent evolution with plants, species of kelp have undergone convergent evolution within their own phylogeny that has led to niche conservatism. This niche conservatism means that some species of kelp have convergently evolved to share similar niches, as opposed to all species diverging into distinct niches through adaptive radiation. A 2020 study looked at functional traits, blade mass per area, stiffness, strength, etc., of 14 species of kelp, and found that many of these traits evolved convergently across kelp phylogeny. With different species of kelp filling slightly different environmental niches, specifically along a wave disturbance gradient. Many of these convergently evolved traits for structural reinforcement also correlate with distribution along that gradient. The wave disturbance gradient that this study refers to is the environments that this kelp inhabit have a varied level of perturbation from the tide and waves that pull at the kelp. It can be assumed from these results that niche partitioning along wave disturbance gradients is a key driver of divergence between closely related kelp. Due to the often varied and turbulent habitat that kelp inhabit, plasticity of certain structural traits has been a key for the evolutionary history of the phyla. Plasticity helps with a very important aspect of kelp adaptations to ocean environments, and that is the unusually high levels of morphological homoplasy between lineages. This, in fact, has made classifying brown algae difficult. Kelp often have similar morphological features to other species within its own area since the roughness of the wave disturbance regime, but can look fairly different from other members of its own species that are found in different wave disturbance regimes. Plasticity in kelps most often involves blade morphology, such as the width, ruffle, and thickness of blades. Just one example is the giant bull kelp Nereocystis luetkeana, which have evolved to change blade shape in order to increase drag in water and interception of light when exposed to certain environments. Bull kelp are not unique in this adaptation. Many kelp species have evolved a genetic plasticity for blade shapes for different water flow habitats. So individuals of the same species will have differences to other individuals of the same species due to what habitat they grow in. Many species have different morphologies for different wave disturbance regimes, but giant kelp Macrocystis integrifolia has been found to have plasticity, allowing for 4 distinct types of blade morphology depending on habitat. Where many species only have 2 or 3 different blade shapes for maximizing efficiency in only 2 or 3 habitats. These different blade shapes were found to decrease breakage and increase ability to photosynthesize. Blade adaptations like these are how kelp have evolved for efficiency in structure in a turbulent ocean environment, to the point where their stability can shape entire habitats. Apart from these structural adaptations, the evolution of dispersal methods relating to structure have been important for the success of kelp as well. Kelp have had to adapt dispersal methods that can make successful use of ocean currents. Buoyancy of certain kelp structures allows for species to disperse with the flow of water. Certain kelp form kelp rafts, which can travel great distances away from the source population and colonize other areas. The bull kelp genus Dreamland includes 6 species, some that have adapted buoyancy and others that have not. Those that have adapted buoyancy have done so thanks to the evolution of a gas-filled structure called the pneumatocyst, which is an adaptation that allows the kelp to float higher towards the surface to photosynthesize and also aids in dispersal by floating kelp rafts. For Macrocystis perifera, adaptation of pneumatocysts and raft forming have made the species dispersal method so successful that the immense spread of coast in which the species can be found has been found to actually be very recently colonized. This can be observed by the low genetic diversity in the subantarctic region. Dispersal by rafts from buoyant species also explains some evolutionary history for non-buoyant species of kelp. Since these rafts commonly have hitchhikers of other diverse species, they provide a mechanism for dispersal for species that lack buoyancy. This mechanism has been recently confirmed to be the cause of some dispersal and evolutionary history for kelp species in a study done with genomic analysis. Studies of kelp structure evolution have helped in the understanding of the adaptations that have allowed for kelp to not only be extremely successful as a group of organisms, but also successful as an ecosystem engineer of kelp forests, some of the most diverse and dynamic ecosystems on Earth. Kelp forests. Kelp may develop dense forests with high production, biodiversity, and ecological function. Along the Norwegian coast, these forests cover 5,800 square kilometers, and they support large numbers of animals. Numerous sessile animals, sponges, bryozoans, and ascidians are found on kelp stipes, and mobile invertebrate fauna are found in high densities on epiphytic algae on the kelp stipes and on kelp holdfasts. More than 100,000 mobile invertebrates per square meter are found on kelp stipes and holdfasts in well-developed kelp forests. While larger invertebrates, and in particular sea urchins, Strongylocentrotus drobachiensis, are important secondary consumers controlling large barren ground areas on the Norwegian coast. They are scarce inside dense kelp forests. Commercial uses. Giant kelp can be harvested fairly easily because of its surface canopy and growth habit of staying in deeper water. Kelp ash is rich in iodine and alkali. In great amount, kelp ash can be used in soap and glass production. Until the LeBlanc process was commercialized in the early 19th century, burning of kelp in Scotland was one of the principal industrial sources of soda ash, predominantly sodium carbonate. Around 23 tons of seaweed was required to produce 1 ton of kelp ash. The kelp ash would consist of around 5% sodium carbonate. Once the LeBlanc process became commercially viable in Britain during the 1820s, common salt replaced kelp ash as raw material for sodium carbonate. Though the price of kelp ash went into steep decline, seaweed remained the only commercial source of iodine. To supply the new industry in iodine synthesis, kelp ash production continued in some parts of West and North Scotland, Northwest Ireland, and Guernsey. The species Saccharina latissima yielded the greatest amount of iodine, between 10 and 15 pounds per ton, and was most abundant in Guernsey. Iodine was extracted from kelp ash using a lixiviation process. As with sodium carbonate, however, mineral sources eventually supplanted seaweed in iodine production. Alginate, a kelp-derived carbohydrate, is used to thicken products such as ice cream, jelly, salad dressing, and toothpaste, as well as an ingredient in exotic dog food and in manufactured goods. Alginate powder is also used frequently in general dentistry and orthodontics for making impressions of the upper and lower arches. Kelp polysaccharides are used in skin care as gelling ingredients and because of the benefits provided by fucoidan. Kombu, kunbu in Japanese, and haidai in Chinese, Saccharina japonica, and others, several Pacific species of kelp, is a very important ingredient in Chinese, Japanese, and Korean cuisines. Kombu is used to flavor broths and stews, especially dashi, as a savory garnish, tororo konbu, for rice and other dishes, as a vegetable, and a primary ingredient in popular snacks, such as tsukudani. Transparent sheets of kelp, oboro konbu, are used as an edible decorative wrapping for rice and other foods. Kombu can be used to soften beans during cooking and to help convert indigestible sugars and thus reduce flatulence. In Russia, especially in the Russian Far East and former Soviet Union countries, several types of kelp are of commercial importance. Saccharina latissima, Laminaria digitata, Saccharina japonica. Known locally as sea cabbage, Morskaya kapusta in Russian. It comes in retail trade in dried or frozen, as well as in canned form and used as filler in different types of salads, soups, and pastries. Because of its high concentration of iodine, brown kelp, Laminaria, has been used to treat goiter, an enlargement of the thyroid gland caused by a lack of iodine since medieval times. An intake of roughly 150 micrograms of iodine per day is beneficial for preventing hypothyroidism. Overconsumption can lead to kelp-induced thyrotoxicosis. In 2010, researchers found that alginate, the soluble fiber substance in sea kelp, was better at preventing fat absorption than most over-the-counter slimming treatments in laboratory trials. As a food additive, it may be used to reduce fat absorption and thus obesity. Kelp in its natural form has not yet been demonstrated to have such effects. Kelp's rich iron content can help prevent iron deficiency. Commercial production. Commercial production of kelp harvested from its natural habitat has taken place in Japan for over a century. Many countries today produce and consume laminaria products. The largest producer is China. Laminaria japonica, the important commercial seaweed, was first introduced into China in the late 1920s from Hokkaido, Japan. Yet mariculture of this alga on a very large commercial scale was realized in China only in the 1950s. Between the 1950s and the 1980s, kelp production in China increased from about 60 to over 250,000 dry weight metric tons annually. In history and culture, some of the earliest evidence for human use of marine resources coming from Middle Stone Age sites in South Africa includes the harvesting of foods such as abalone, limpets, and mussels associated with kelp forest habitats. In 2007, Erlandson et al. Suggested that kelp forests around the Pacific Rim may have facilitated the dispersal of anatomically modern humans following a coastal route from Northeast Asia to the Americas. This kelp highway hypothesis suggested that highly productive kelp forests supported rich and diverse marine food webs in nearshore waters, including many types of fish, shellfish, birds, marine mammals, and seaweeds that were similar from Japan to California. Erlandson and his colleagues also argued that coastal kelp forests reduced wave energy and provided a linear dispersal corridor entirely at sea level, with few obstacles to maritime peoples. Archaeological evidence from California's Channel Islands confirms that islanders were harvesting kelp forest shellfish and fish, beginning as much as 12,000 years ago. During the Highland clearances, many Scottish Highlanders were moved on to areas of estates known as crofts, and went to industries such as fishing and kelping, producing soda ash from the ashes of kelp. At least until the 1840s, when there were steep falls in the price of kelp, landlords wanted to create pools of cheap or virtually free labor, supplied by families subsisting in new crofting townships. Kelp collection and processing was a very profitable way of using this labor, and landlords petitioned successfully for legislation designed to stop emigration. The profitability of kelp harvesting meant that landlords began to subdivide their land for small tenant kelpers, who could now afford higher rent than their gentleman farmer counterparts. But the economic collapse of the kelp industry in northern Scotland during the 1820s led to further emigration, especially to North America. Natives of the Falkland Islands are sometimes nicknamed kelpers. This designation is primarily applied by outsiders rather than the natives themselves. In Chinese slang, kelp, simplified Chinese hai dai, is used to describe an unemployed returnee. It has negative overtones, implying the person is drifting aimlessly, and is also a homophonic expression, Chinese hai dai, literally sea wading. This expression is contrasted with the employed returnee, having a dynamic ability to travel across the ocean, the sea turtle, simplified Chinese hai gui, and is also homophonic with another word, simplified Chinese hai gui, literally sea return. Conservation. Overfishing nearshore ecosystems leads to the degradation of kelp forests. Herbivores are released from their usual population regulation, leading to overgrazing of kelp and other algae. This can quickly result in barren landscapes where only a small number of species can thrive. Other major factors which threaten kelp include marine pollution and the quality of water, climate changes, and certain invasive species. Interactions. Some animals are named after the kelp, either because they inhabit the same habitat as kelp or because they feed on kelp. These include northern kelp crab, Pugetia producta, and graceful kelp crab, Pugetia gracilis, Pacific coast of North America. Kelpfish, blenny, for example, Heterosticbus rostratus, genus Gibbonsia, Pacific coast of North America. Kelp goose, kelp hen, Chloephaga hybrida, South America and the Falkland Islands. Kelp pigeon, sheathbill, Chionis alba and Chionis minor, Antarctic.